Hello again. In this video, I'm going to go over section 3.8, which is about implicit differentiation. Now, to illustrate this idea of implicit differentiation, I'm going to go over an example. And in this example, we're going to find the derivative of y with respect to x in two different ways. The first way we're going to find it is using explicit differentiation, and then we'll find it using implicit differentiation. Okay, so in this particular example, we have x times y is equal to 4, and we want to find the derivative of y with respect to x using explicit differentiation. Well, to find the derivative of y with respect to x using explicit differentiation, the first thing we have to do is isolate y. Well, that's easy enough to do. All we have to do here is divide by x, right? And we get y is equal to 4 over x. And then after you isolate the y, what we're going to do is we're going to take the derivative of both sides of this equation with respect to x. Okay, so on the left-hand side, that's just going to leave us with dy dx. And on the right-hand side, we're going to have to find the derivative of this function 4 over x with respect to x. Now remember, whatever you do to one side of the equation, you can do to the other side of the equation and it would remain equal. So as long as we take the derivative of both sides of this equation, they should still be equal on both sides. Okay, so let's find the derivative of this 4 over x. Okay, to do that, we're going to have to use the quotient rule. And remember, the quotient rule says take the low and multiply it by the derivative of the high, minus the high times the derivative of the low, divided by the low times the low. Okay, so take the low times the derivative of the high, which of course is 0, since that's a constant, minus the high, which is 4, and then the derivative of the low with respect to x would be 1. All over low times low, so x times x, which we can just write as x squared. Okay, and so if we simplify this, on top we just have 0 minus 4, so that's minus 4 all over x squared. Okay, so that's the derivative of y with respect to x. Okay, let's do the same problem, but this time we're going to find dy dx using implicit differentiation, which is what this section is about. Okay, so if we're going to find dy dx using implicit differentiation, what we're going to do first is not isolate y. We're going to ignore the first step that we did when we did it explicitly. The reason it's called explicit differentiation is because you have to explicitly solve for y before you find the derivative. If you're going to do it implicitly, we skip that step. And so our first step here is to simply take the derivative of both sides with respect to x. We skipped the first step that we did before, and we jump to the second step. Okay, so we're just going to take the derivative of both sides of this equation with respect to x. Okay, so on the right-hand side, that's not too difficult. The derivative of 4 would be 0, since it's a constant. Now, the right-hand side, we have to be careful about how we find this derivative. Notice that these are being multiplied. And so if we're going to find the derivative of this, we're going to have to use the product rule. Okay, and the product rule says you take the first function and you multiply it by the derivative of the second function, and then you add that to the second function times the derivative of the first function. Okay, so let's find that derivative using the product rule. Okay, so we take the first, which is x, times the derivative of the second function, which is y, with respect to x. And that's just going to give us dy dx, right? The second function is y, and we're taking the derivative of that with respect to x. Plus the second function, which is y, times the derivative of the first function, which is x, but with respect to x. And of course, that derivative would be 1. Okay, so on the left-hand side, using the product rule, this would be the derivative of x times y with respect to x. Okay, and then the final step is to solve for dy dx. After all, that's what we're trying to find. Okay, well, if you want to isolate dy dx here, you first have to subtract the y. To the right-hand side, and then you have to divide by x. Okay, so we're left with dy dx is equal to negative y over x. Now, typically what's going to happen when you use implicit differentiation is you will be left with a derivative, like dy dx, written in terms of both x and y. The reason that's the case is because the reason we usually use implicit differentiation is because we can't isolate y. In the cases when we can't isolate y, we cannot use explicit differentiation, but we can still do it implicitly. And so the reason you're probably doing implicit differentiation is because you can't isolate the y. And if you can't isolate the y, then you can't substitute for it when it appears in your derivative. And so typically, if you're going to use implicit differentiation, your derivative, dy dx, will be a combination of both x's and y's. It'll have a combination of both variables. But in this case, I'm picking a problem where we can isolate y, right? We've already done that. We know y is equal to 4 over x. Okay, so if you were to give me this problem, I probably wouldn't find dy dx using implicit differentiation. I would use explicit differentiation because I can isolate the y, like we did in part A. But let's just see if we get the same answer. So we know y is equal to 4 over x, so we can replace this y. So that would be the same as 4 over x divided by x, since y is 4 over x. And then if you wanted to simplify this, you can think of this as being x over 1. When you divide a fraction by another fraction, you can flip the bottom fraction and multiply by it. So let's just flip this, and that's going to be 1 over x, and then multiply by that reciprocal. Okay, and so that ends up giving you minus 4 over x squared, which is exactly the same answer that we had when we did it explicitly. So we get the same answer either way, whether we find dy dx explicitly using explicit differentiation or we find it using implicit differentiation. Now, once again, just to clarify, if you can solve for y, right, if you can isolate y like you can in this case, then you're probably going to find dy dx using explicit differentiation. So implicit differentiation will probably only be used in cases where you cannot isolate y. And so the examples we're going to see in the rest of this section are going to be cases where we can't get y by itself, where we can't isolate the y. But that is not going to be an obstacle for finding dy dx. We can still find dy dx, but we just have to do it using implicit differentiation instead of explicit differentiation. And what's going to happen is you'll get to this step right here where you solve for dy dx, and it's likely that you'll have a combination of x's and y's in your derivative. And you won't be able to replace the y because you can't isolate y. That's the reason you're using implicit differentiation in the first place. But we accept that. We accept the fact that when we use implicit differentiation, we're likely to end up with a derivative that has both x's and y's in the derivative. That's just the price we pay for using implicit differentiation. We would prefer our derivative to be written just in terms of x, but that's only possible if we can substitute for the y, and the only way we'll be able to substitute for the y is if we can isolate it. And again, the reason we're probably using implicit differentiation in the first place is because we can't isolate the y. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.